Hello students, myself Dr. Sucharita Bhattacharya, Associate Professor of Physics from Guru Nanak Institute of Technology, is starting my lecture series on electromagnetic theory for Physics 2, that means second year, third semester BTech course. The streams under consideration is Computer Science and Engineering and Information Technology. So today I am starting with first lecture, that is lecture 1. To start with, let me introduce the syllabus of the Physics 2 first. The code is PH301. The contact is 3 lectures per week and credit is 3. Total number of lectures allocated here is 36. Now, I am starting with the module 4, that is the electromagnetic theory, where we have total 11 lectures. Now the entire module 4 is subdivided into 4 divisions or 4 sub-modules rather. The first one is 4.01, that is electrostatics, where we are going to discuss Gauss's law in integral form and conversion into differential form, equation of continuity, the Poisson's and Laplace's equation, the application to parallel plate spherical and cylindrical capacitors for the boundary value problems. Now there we will consider 3 lectures. Next, for the submodule 4.02, we will discuss the magnetostatics, where Lorentz force and definitely the concept in Hall effect, force on a small current element placed in a magnetic field, the Biot-Savart's law, and hence to show the non-existence of magnetic monopole, Ampere-Circuital law, and the transverse nature, Ampere-Circuital law and magnetic vector and scalar potential we will discuss. There also we have considered 3 lectures. Next, coming to the submodule 4.03, where we are going to discuss the time varying fields and the Maxwell equations. It will include Faraday's law, the concept of displacement current, Maxwell's field equations with physical significance, wave equations in free space, and transverse nature of electromagnetic wave. There we need 2 lectures. Last submodule is 4.04, where we are going to discuss about the electromagnetic wave and polarization, where the definition of polarization, plane of polarization, plane of vibration, Malus's law, the fundamental concept of plane, circular and elliptic polarizations, obviously the qualitative idea with examples, as well as we will discuss the Brewster's law, double diffraction, including ordinary and extraordinary rays, then Nichols prism and engineering applications in electromagnetic theory, and obviously the numerical problems will be included there. Now, next question naturally arises to you as student, that what about the course objective of this electromagnetic theory? Electromagnetic theory will provide you the exposure to the foundations of obviously electrostatics, magnetostatics and electromagnetic induction, which ultimately help to reach you the Maxwell's field equations, thus highlighting the nature of electromagnetic wave, including their polarization property, very, very important one. And this knowledge is applied in communication and networking. Now, the next question naturally arises, that what about the course outcome? That means after completion of this course, what students will learn to do? They will be able to understand and explain the phenomenon of electrostatics, magnetostatics and electromagnetic theory. They can apply the knowledge of electromagnetic theory in communication and networking. They can also analyze the change in electric and magnetic fields in various systems. Naturally, next question comes to your mind, that what about the books we have to follow? Here, I have given 8 standard text and reference books, including the 2 books on optics by very famous 2 authors, A.K. Ghatak and by B.D. Gupta, along with the books on electromagnetics, including Loud's book, the B. Ghosh, Chattopadhyay Rakshit, then Griffith, Sadiku. These are very standard books. All are available in the library. In addition to these subject books, you can take a look to general textbooks on integrated engineering physics by different authors, very famous one, and publishers are good. You can take a look on the electromagnetic theory chapter from this book. For the detail of the syllabus and the books, you can consult our website, that is www.gnit.ac.in syllabus. Let us now start our today's lecture. Today I am starting with the prerequisite of this chapter on electromagnetic theory. And this prerequisite consists of the first year knowledge of vector calculus and its basic rules. Actually, vector calculus and its basic rules here is working as the mathematical tool to move in electromagnetic theory, without which we cannot move here. Now to start with, we all know that all physical quantities surrounding us are divided into scalars and the vectors. Time, temperature, mass, potentials, which have magnitudes only and represented by numbers with suitable unit of measurements, are known as the scalar quantities. On the other hand, velocity, acceleration, force, field intensities, which have both magnitude as well as direction and represented by directed line segments, are called the vector quantities. Now, to study the vector, we have to concentrate on vector algebra as well as vector calculus. Vector algebra already is done in HS course, and vector calculus, as I already mentioned, it was discussed in first year mathematics, but here we will recapitulate it, but including physical meaning. That is very, very important. In first year mathematics, you have been given the definitions and the operation part, but not the physical part. Now to start with vector calculus, we have to do two things. First is vector differentiation, then vector integration. Now, what about vector differentiation? If a vector function changes continuously with respect to a scalar variable, both in magnitude and direction, then in general we say that vector is differentiated with respect to that scalar. That means dA dt, mind it, all vectors I will consider here in terms of the bold letter, and the scalar the regular one. So dA dt means differentiation of vector A with respect to t, the time scalar one. It is written as limit of delta t tends to 0 del A del t equal to limit of delta t tends to 0 A at t plus delta t minus A at t by delta t. What about the meaning here? Let us take a look. AT is a vector. It is representing both in magnitude and direction the vector A at time t. Similarly, A at t plus delta t is represented by A at t plus delta t line. So what about this? This is delta A in time delta t according to the law of triangle of addition of triangles. So in the limit delta t tends to 0 dA dt, what does it represent? Delta A by delta t. So delta A by delta t in the limit delta t tends to 0 means it is along the tangent to this curved path. We are considering the curved path because AT and AT plus delta t, they are not same. So they are connected by a curved line. In the limit delta t tends to 0, we are getting this change delta A in the limit delta t tends to 0 at this point, which is nothing but representing the direction as tangent to this curved path, and which is nothing but physical meaning of the vector differentiation. Now let us come here. The vector differentiation using more than one scalar variable. Previously we considered one scalar variable, that is the time. Here we are considering three scalar variables, that is the space coordinates x, y, z. So if a vector A depends on three space coordinates, the scalars x, y, z, then we can write A as function of x, y, z and look at the change in the derivative. First one, del A del x equal to limit of delta x tends to 0, A at x plus delta x y z minus A at x y z divided by delta x. Just look at our previous slide. So the same definition we are following here, here we have the single variable, that is t, and this is the definition. But in this case we have the three variables. In the first one, we are varying a with respect to x, keeping yz fixed. That's why here we are getting the change x plus delta x, yz remaining same, and here it is x, yz by delta x in the limit delta x tends to 0. So it is a partial derivative of a with respect to x. Look at the symbol, it is del x. Now come to the second one. Here we are taking the change with respect to y, keeping x and z fixed. So corresponding derivative is represented by del a del y. Limit of delta y tends to 0, ax y plus delta y z minus a at x y z divided by delta y. In the limit, obviously delta y tends to 0. Similarly, the third one, the partial derivative of a with respect to z, where x and y are remaining same, only z is varying. It is represented as a x y z plus delta z minus a x y z divided by delta z in the limit delta z tends to 0. That means these three are called the partial derivatives of a with respect to x, y and z respectively, provided the limits exist. Now, if we consider Txyz as a scalar point function, say temperature. Here we consider Axyz as vector point function. Here we are considering Txyz as a scalar point function, say temperature, where all three variables are changed by infinitesimal amounts dx, dy and dz. Then the total change of T, is represented as dt equal to del x of t into dx plus del y of t into dy plus del z of t into dz. Here, del x, del y and del z operating on t are called scalar operators with respect to x, y and z. Naturally, if you associate I cap with del x, j cap with del y and k cap with del z, where I cap, j cap and k cap are unit vectors along x, y, z, then we will get corresponding vector operators. That means I cap del x, j cap del y and k cap del z are vector operators corresponding to scalar operators del x, del y and del z. And here it is the total change in t if xyz changes by infinitesimal amounts dx, dy, dz, and it is represented in terms of operators. Now, from these three important vector operators, we can define most importantly the vector differential operator del or nabla in the form del equal to I cap del x plus j cap del y plus k cap del z, without which we cannot move in electromagnetic theory anymore. I am repeating this line. The sum of the three vector operators, that is I cap del x, j cap del y and k cap del z, is called the vector differential operator del or nabla, without which we cannot move in electromagnetic theory anymore. Now, next we will going to introduce three primary operations of del, three primary or basic operations of del in the form of the gradient, the divergence and the curl, without which the nature of electric and magnetic field from physical point of view will not be clear. I am repeating this statement once more. Three primary or basic operations of del now we are going to introduce, which will help us to understand the nature of electric and magnetic fields from physical point of view. After that, we will discuss some secondary operations of del or nabla, whose importance also will be clear to you.
Yes.
So students, let us start the three primary operations of del, the nabla vector differential operator. So, to start with, let me talk about the gradient first. What do we mean the gradient? If phi xyz is a differentiable scalar field, that means if phi xyz is defined at each point xyz in a certain region of space and it can be differentiated there, that means it is a differentiable scalar field, then its gradient is defined as grad phi. This is the symbol grad phi, where we have seen that grad is equal to I cap del phi del x plus j cap del phi del y plus k cap del phi del z. So that grad operator will operate on phi in the form of the gradient. So let us take a look how it looks like. I cap del del x on phi plus j cap del del y on phi plus k cap del del z on phi. Now look at, in each case, I cap, j cap, k cap, they are unit vectors along the direction of x, y and z. So gradient operator operating on scalar field converts it ultimately into a vector field. So del operating on a scalar point function represents a vector. That is very, very important. So gradient operation converts a scalar into a vector. Now physically, what about the meaning of the gradient? Physically, it represents the maximum space rate of variation of phi both in magnitude and direction. Basically, it is representing the variation of phi with respect to x, with respect to y, with respect to z. That means space rate of variation, there is no doubt about it. And magnitude wise, it is the maximum space rate of variation of phi, and both in magnitude as well as in direction. Now what about that direction? This direction is normal to the level surface of the scalar field phi equal to c, a constant. Actually phi equal to c, that means the potential if constant on a particular surface at each and every point, then that surface is termed as level surface corresponding to that scalar field. And the direction of the gradient is perpendicular to this level surface of the scalar field phi xyz equal to constant at each and every point. Now, most importantly, let us have some idea about the concept of potential to be introduced in detail in electrostatics first with the gradient. Just look at the form of the gradient, grad phi, and it is representing a scalar field. Now, if it is representing a vector field, I am sorry. Now, if that vector field is considered to be A, say, it is obtained as gradient of a scalar field. So, how to represent it? Grad phi equal to A, where A is a vector field. In that form, phi is called the potential function of the vector field A. That means the vector field A can be obtained from the phi using gradient operation. In that case, phi will be called the potential function corresponding to the vector field A. It is a very general definition and general expression we will discuss in detail during the electrostatics as well as in magnetostatics too. So, if we can represent gradient phi equal to A, the scalar field, then phi is called the potential function corresponding to the vector field A. So, grad is working on scalar to make it a vector. It holds for a conservative vector field. The additional information very, very important. This vector field in this form, if obtained, then it is called a conservative vector field. That means for which the energy of a body remain conserved in moving in a closed cyclic path. So for conservative vector field, the energy of a body remains conserved in moving in a closed cyclic path. Most common example of this type of conservative vector field using the concept of potential in electrostatics, it is the electrostatic field itself, where we will find in our due course that E can be expressed as negative gradient of potential. Negative gradient of potential. This negative sign is coming here because we will find that electric field and potential, their directions are just opposite. That's why if you don't consider this negative sign right now, you will find other things remaining same. That is, electric field is expressed as gradient of potential P. P is potential, E is vector field. So gradient operating on P makes it a vector, and negative sign is coming because electric field and potential are in the opposite direction. Let us now move to the second operation, that is the divergence. For divergence, in place of a scalar field, we consider a vector field, that is A equal to IAX plus JAY plus KAZ, which is a differentiable vector field. That means it is defined at each and every point in a certain region of space. At the same time, it is differentiable there. So it is a differentiable vector field. Then divergence of this vector field is expressed as div A. A is a vector, it is written in bold, or del dot A, or del dot A. So both are vector, both are vector. So del dot A means I cap del del x plus j cap del del y plus k cap del del z dot A. A means IAX plus JAY plus KAZ. So del dot A when operate, we will expect a scalar out of it because both are vectors and their dot product or scalar product is taken. So we will expect a scalar. Let us check it. So I dot I, J dot J and K dot K, according to the basic rule of vector, gives us 1. In other cases, that is I dot J, I dot K, or J dot I, J dot K, and K dot I, K dot J will be 0. So if you take I dot I, what you will find? Del del x of X. Next, J dot J, del del y of AY. Next, K dot K, so del del Z of AZ. That means we are getting a scalar that is expected because we are taking a dot product. So because of divergence, we are taking dot product between del and the vector field, and the net result is a scalar. In case of the gradient, what we got? We took the grad operator or del operator on phi, the scalar, to make it a vector. So this is a basic difference. Now let us come to the physical meaning. Physically, divergence of a vector field at some point represent that how much a field diverges or emanates or spreads out from that point, which is considered to be the source point, and here divergence of the field is positive. Actually, in physics, the terminology very much related to the meaning of literature. So we all know what about the meaning of divergence in literature. Similarly, it is very much applicable in our case. The divergence of a field at some point represent how much a field diverges, emanates or spreads out from that point, which is considered to be the source point, and here divergence of the field is considered to be positive. Let us take a look at figure 1. It represents the divergence of a vector field with respect to some point P. The field lines are diverging or spreading or emanating out as if there is a source point. So here divergence of the field is positive and P is considered to be the source point. On the other hand, if the vector field meets or converges at some point, that means opposite to divergence, the field is considered to have Definitely negative divergence, and the point is considered to be the sink point. I am repeating, if the vector field meets or converges at some point, the field is considered to have negative divergence and the point is considered to be the sink point. Let us look at second figure. Now all the vector lines, they are meeting here. They are meeting here. So with respect to this point P, that means the point P, the field has negative divergence, and with respect to this point P, the point P will be called the sink point. In case of sink, how the things are going in. The third case is very interesting. If the field neither diverges nor converges, then del dot A equal to 0. If the field neither diverges nor converges, del dot A equal to 0, and the field is called in that case the solenoidal field. Field is called the solenoidal field. The third case is shown here. Just take a look at the appearance of the field. It is solenoidal, just like the solenoid. The most common example of this type of solenoidal field is vector in case of the magnetostatics, that is the magnetic field, or induction vector B, for which we used to get del dot B equal to 0. That will be discussed in our due course. So most common example of solenoidal field is the magnetic field or induction vector B, for which del dot B equal to 0. So this is the second operation. Let us now move to the third operation involving del, the curl or rotation. The curl or rotation, again the name is very much meaningful. If, just like the previous case, A equal to Ix plus Jy plus Kz is a differentiable vector field, then its curl or rotation is expressed as curl A or rot A, that is del cross A. Previously it was del dot A, it is now del cross A. So we are writing the same expression, I cap del del x plus j cap del del y plus k cap del del z, and Ix plus jy plus kaz, but involving cross sign in between. Now what about the operation Gibbs? Now we all know how to take care of cross multiplication, that is I cap, j cap, k cap in the form of determinant, we write it, then del del x, del del y and del del z, and then ax, ay and az. The three components are written like that. At the top we write the three unit vectors along x, y, z, and at the bottom we write them like this. Then how to take it? I cap times del del y of az minus del del z of ay, plus j cap times del del z of ax minus del del x of az, plus k cap times del del x of ay minus del del y of ax. In all cases, I cap, j cap and k cap are involved, so this is a vector. So curl represents a vector. Physically, it means that how much a vector rotates or curls around some point. Rotates or curls around some point, say P here. Obviously, a vector field whose curl or rotation is 0 is called the irrotational vector, for which del cross A equal to 0. So if curl is 0, then the vector is called irrotational vector, because rotation is 0, for which del cross A is 0. An irrotational field is also conservative field. We will find in our due course, and most common example is the electrostatic field, that is del cross A equal to 0. Most common example is the electrostatic field, that is del cross A equal to 0. Next we will come to the second derivative using del or nabla. So far we have considered all first order derivative in terms of the gradient, the divergence and the curl. Now we will come to the second derivatives using del or nabla. Now using second derivative and on del or nabla, we will consider here three different cases. First one is the divergence of gradient. Divergence of gradient. So let us take a look here. Del dot del phi. This is divergence, means dot product is coming, del dot something is divergence, already we have seen it. And what about gradient? Grad phi. So del dot del phi will give us ultimately del square phi, because del means I cap del del x plus j cap del del y plus k cap del del z dot grad phi. What about grad phi? We already have done I cap del phi del x plus j cap del phi del y plus k cap del phi del z. Now how to take care of them? We know that I dot I, j dot j and k dot k will come into consideration. Accordingly, we will get del square phi. That means del del x of del phi del x plus del del y of del phi del y plus del del z of del phi del z. That will give us del square phi, where obviously del square will be del 2 del x2 plus del 2 del y2 plus del 2 del z2, the so-called Laplacian operator. The so-called Laplacian operator. Actually, the derivation I am not showing it here in detail because it is a recapitulation class I already mentioned, and these things you have done already in first year mathematics. So this is divergence of gradient, which gives us a new variable, new operator rather, that is Laplacian operator. Mind it, it is a scalar operator because del dot del you are taking, so ultimately at the end you are getting a second order derivative, but it is a scalar one. Now two very important other operations. One is the curl of gradient, that is del cross del phi. It will give us 0. Curl grad always give us 0. Curl of grad. If you do in your copy at home, very easy. Grad phi already introduced, and already curl operation is introduced to you. So definitely you can get that del cross del phi equal to 0. Next is divergence of curl, another different operation. Divergence of curl, del dot del cross A. This is the curl operation and then the divergence is taken on it. So we are getting divergence of curl, it will come out also 0. So the three very important operations including second order derivatives of del or nabla is shown here. Divergence of gradient introduces us Laplacian operator, that is del square phi. Curl of gradient always comes out to be 0. Divergence of curl always comes out to be 0. Let us now move to the vector integration. So we are recapitulating vector calculus. So vector differentiation part done. Now we are moving to vector integration. This will give us the two important theorem. The vector integration, the basic idea we will discuss first, and then its applications in theorems we will consider, which will help us to understand the use of vector calculus in the study of electromagnetic theory more clearly. So with differentiation, vector differentiation, there is an element of incompleteness. So vector integration will give us the complete idea that how to apply vector calculus in electromagnetic theory in terms of two very important theorems used in vector integration. Before going to the theorem part, let us come to the definition of vector integrations one after another. First one is the line integral. Line integral of a vector point function I equal to Iax plus Jay plus Kaz along a curved path C between two endpoints 1 and 2 is defined as the integral of its tangential component along C and is represented by I equal to line integration over C A dot dr equal to integration 1 to 2 A dot dr. Let us take a look at the figure. This is a curved path along which a vector field A is taken. The curved path is C. It is actually moving between two endpoints 1 and 2. So what about line integration? Any integration taken along this curved path is called the line integration. How it forms looks like, that is A dot dr along C you can write, or you can write 1 to 2 because the two endpoints are from 1 to 2 along this curved path C. Now, as an example of this line integration, if we consider the vector field as a force field, here I have written it as A. In place of A, you can write it as a force field, because force is an example of a vector field. So if we consider the vector field as a force field working on a particle moving along this curved path. So a particle is moving along this curved path, and we are considering this around this curved path we have a force field which is working on this particle which is moving along this curved path. Then what about the corresponding line integration? I will be equal to integration over C, but in place of A, here we are writing F, that is the force field. So F dot dr. F dot dr 1 to 2, you can write it integration. It is nothing but the work done. Very much known to you from your school level. So this is the very famous and very common example of line integral, that is F dot dr gives us the work done on a particle moving along the curved path in a force field. If the field is conservative, I am again coming back to the same point because it is very, very important so far as electromagnetism is concerned, that conservative force field. If the field is conservative, then line integral will be independent of the path of integration, provided endpoints remain fixed. That means between the 2 points 1 and 2, if remains fixed, you can have the line integration value same whatever may be the path. We will find it in our electrostatic course. I am repeating this part once more, that line integral will be independent of path of integration if the field is conservative, provided endpoint remain fixed. That is I equal to 1 to 2 along C. Here we have taken 2 paths between the 2 fixed endpoints. 1 to 2 along C F dot dr is found to be equal to 2 to 1 F dot dr along B. So line integral 1 to 2 along C F dot dr, if equal to the line integral along B between 2 to 1 on F dot dr, then the corresponding force field F will be called the conservative force field. That means line integral is independent of the path. Whatever path you take, line integral value is same, magnitude is same, only you are taking different direction. So one will be the opposite in direction with respect to the other. That means in a conservative force field, what about the total work done in a closed path? That means 1 to 2 plus 2 to 1. That will be given by closed line integration F dot dr equal to 0. It is 1 to 2. Next you do plus 2 to 1. 1 to 2 plus 2 to 1. And one is going along this direction, other will go along this direction, and the value of the line integral are same. So when you just add them, so what you will get? The closed loop integration F dot dr equal to 0. Electrostatic field E is an example of such a conservative field. Electrostatic field E is an example of such a conservative field. That means in case of any ordinary force field, if you consider the force field is the electrostatic field, then for that this total integration, line integration, closed line integration will be 0, which is a property of the conservative vector field. Now let us come to the case of surface integration. Let us come to the case of surface integration. It is expressed over a simple surfaces, obviously in space, inside which a vector field A is defined. So surface integration, obviously a surface integral is expressed over a simple surface S in space inside which a vector field A is defined. It is expressed as the integral of the normal component of A across the surface. So I equal to A dot ds surface integration. So 2 integration is representing here the surface integration. A dot ds. This ds is called the aerial vector. it can be written as A dot n cap ds. That means here ds is the magnitude of that ds vector, and n cap represent the unit vector which is perpendicular to this ds vector, representing the aerial vector as a whole as ds vector. It is represented here that this is a surface on which a differential of surface is taken, that is delta s. This is the n cap unit normal on it. So, and this is A. So, A dot ds means the angle theta is included here. For a closed surface, you can use this closed loop on double integration A dot ds. In place of double integration, using a single integration with S here, that means the surface, you can use the surface integration also. Now, most common example of surface integral in electromagnetic theory is closed loop surface integration E dot ds and B dot ds, the so-called electric and the magnetic flux. Actually, A dot ds represent the flux of the vector field A. In place of A, we are considering specifically electric field and the magnetic field. So, E dot ds and B dot ds represent the electric and the magnetic flux, which we will study in detail in electromagnetic theory. Now let us come to the case of the volume integration. It is expressed on scalar function as well as on vector function, that is phi xyz as well as vector function axyz over a volume V enclosed by a closed surface S. Over a volume V enclosed by a closed surface S, and volume integration is written as phi dV using triple integration, or A dV using triple integration means volume. You can use a single integration with V. Single integration with V also represent the equivalent volume integration. As an example of a volume integration, let us now consider a scalar field. Still now we have always considered the vector field. Let us take here a scalar field. It's a density of a substance whose volume integral. So if phi is represented by rho, the density of a substance, then rho dV, volume integration, represent mass of that substance. So as an example of volume integration, let us consider the density of a substance, a scalar field, whose volume integration represent the mass of that substance. Now the two very important vector integration theorem without which we cannot move in our present electromagnetic theory are now represented here, one with which you are also familiar in the first year mathematics course, but I am recapitulating. First one is Gauss's divergence theorem. It represents the volume, it actually relates rather the volume and the closed surface integration. So what about the statement that volume integration of divergence of a vector field is equal to the closed surface integration of that vector field? Volume integration, closed surface integration of that vector field. That means if we consider a closed surface S enclosing a volume V, then divergence of any vector field defined inside that surface and volume is equal to the surface integration of the flux of that vector field. So that is the Gauss's divergence theorem, because divergence is there and it is relating volume and surface integration. Next is the Stokes theorem. It relates the closed loop integration with surface integration, open surface. If we consider an open surface enclosed by a closed loop, then according to Stokes theorem, the closed loop line integration A dot dr on a vector field defined in that space is equal to the surface integration of its curl. The surface integration of its curl. That means this is relating the closed loop integration with open surface. Open surface enclosed by a closed loop, then closed loop line integration is equal to the surface integral of curl of that vector field defined there. And another point we have to discuss, that is curvilinear coordinate system later on. So, thank you students.